Hello, welcome to e-learning in Honors Precal. I hope everyone had a good break and that you're all staying healthy. Today we're going to begin exploring some basic concepts in probability. This video lesson exactly parallels the material from the chapter, so you may prefer to read that either online or from the PDF capture that's available to you from our shared Google Drive. To start off, let's consider what we mean by the word probability. If I flip a fair coin, I know that it can come up either heads or tails. I might even know that the probability of it coming up heads is 1/2 or 50%. But what does that mean? Does it mean if I flip a coin twice, it will come up heads once and tail once? Let's look at the following table. This table shows what happens as we flip a larger and larger and larger number of coins over time and keep track of the percentage of heads that have occurred up to that point. So you can see when I have flipped exactly one coin, it came up heads, and that's 100% heads so far. By the time I flipped 5 coins, note that 4 of them were heads, so that's 80%. But as the number of coins flipped gets even higher, say up to 100, the percentage of heads has dropped down to 54%. This leads us to a definition. The probability of an event E is the value that its relative frequency of occurrence approaches in the long run. So in the case of flipping a coin, in the long run, as we flipped hundreds or thousands of coins, of an event E, the percentage of value that its relative frequency of occurrence approaches and in the long run would be what we would say is the probability. In the case of the coin flips, probability is 50% that it will come up heads. Now let's see how your intuition about probability hundreds or thousands of coins. Let's find the probability of the number of heads approaches 50% of tossing 2 heads in a row. Let's see how our intuition about probability holds up. Drawing a queen from a standard deck of 52 cards, rolling a sum of 4 on a single roll of 2 fair dice, or having tendinitis if your doctor tells you that further tests are needed to determine whether your sore knee is caused by tendinitis, bursitis, arthritis, or a torn meniscus. For A, I've flipped 2 coins, or 1 coin twice in a row, and each of the flips has 2 possible outcomes. So by the multiplicative principle of counting, there are a total of 4 possibilities. These are head, 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 tail, tail, head, and tail, tail. Of these, only one of the 4 comes up 2 heads in a row, so the answer to A is 1/4. For B, there are 4 queens in a standard deck of 52 cards, so the probability of getting a queen would be 4 out of 52, which is 1/13. C is a little bit surprising at first. Again, using the multiplicative principle of counting, the first die could come up any of 6, the second could come up any of 6, so there are a total of 6 times 6, or 36, outcomes. How many of these yield a sum of 4? Well, that could be a 1 and a 3, a 2 and a 2, or a 3 and a 1. So a total of 3 out of 36, or 1/12, is the probability of rolling a 4. Finally, for D, we don't know the relative frequencies of tendinitis, bursitis, arthritis, or torn meniscus, so we can't assume they're equally likely. So the answer to D is we just don't know. Let's suppose we're conducting an experiment like flipping a coin or rolling dice or drawing cards. The set of all possible outcomes of the experiment is called the sample space. An event is any subset of the sample space. Here's a very important formula. If in a finite sample space all of the outcomes are equally likely, the probability of an event E, written P of E, is given by this formula. It's possible to divide up the sample space, that's the set of all possible outcomes, by using the concept of random variables. Consider an experiment in which we roll two distinguishable dice. Perhaps one is red and one is blue. Since there are 6 outcomes for each, again by the multiplicative principle of counting, there are 36 outcomes in the sample space shown here. Notice how the outcomes are listed as ordered pairs. 3, 2, for example, indicates that ordered pair 3, 2 indicates that the first die came up 3 and the second die came up 2. There are several different ways to associate numbers called random variables with these 36 outcomes. One way is to use the random variable, which is the sum of the two numbers, as shown here. Notice in each case, the value in the table is the sum of the two. For example, our earlier roll of 3, 2 now corresponds to a value of 5. We'll come back to this scenario in a moment, but there are a couple of other random variables we could have used. In the scenario shown, the random variable is the product of the numbers on the two die. Here's another situation in which I use the first die as the tens digit and the second die as the ones digit. So in the 3 examples, die rolls of 2 and 3 could have corresponded to a sum of 5, a product of 6, or a new number of 23. In each case, we get a different random variable. Let's return to the situation in which we're creating a random variable, which is the sum of the numbers on the two dice. Now the outcomes aren't the ordered pairs anymore, they're the sum of the ordered pairs. And notice that they're not all equally likely. A sum of 2 only happens one way. A sum of 3 can happen 2 ways, either a 1 and a 2 or a 2 and a 1. A sum of 4 can happen 3 different ways. That would be a 3 and a 1, a 2 and a 2, or a 1 and a 3. The most likely outcome with this random variable, the sum of them, is a 7. The event getting a 7 is the sum of the numbers on two dice, has a probability of 6 out of 36. So the key thing to be aware of here is the outcomes in the original table, ordered pairs of the numbers, are all equally likely. But when I look at the random variable, which is the sum of the outcomes, that random variable is not distributed equally. Let's go ahead and take a look at a chart which sums up the likelihoods in this scenario. The 2-column table shown on the right shows the relative probability of the outcomes of a sum of 2 through 12. Notice 2 and 12 are quite unlikely, with happening 1 out of 36 times on average each, whereas 7 can happen 6 out of 36 ways. Here's a new problem to consider. We wish to find the probability that the sum of the two dice is divisible by 3. The solution is that the event E consists of the following outcomes: 3, 6, 9, and 12. The only 4 sums that you can get on rolling two dice that wind up being divisible by 3. Let's see what their individual probabilities are. Probability of getting a 3 can happen 2 ways: 1 and 2, or 2 and 1. Probability of getting a 6 is 5 out of 36. You could get 1 and 5, 2 and 4, 3 and 3, 4 and 2, or 5 and 1. The probability of getting a 9 is 4 out of 36. You could get a 3 and a 6, a 4 and a 5, a 5 and a 4, or a 6 and a 3. Finally, the probability of a 12, that can only happen one way, so that's 1 out of 36. I add up all these probabilities together, and I get 12 over 36, or 1/3. Not every function that assigns numbers to outcomes qualifies as a probability function. Here's the definition. A probability function is a function p that assigns a real number to each outcome in a sample space S and subject to the following conditions. For every outcome O, the probability of O must be a number between 0 and 1. 2. The sum of all the probabilities of all outcomes in the sample space must be 1. 3. The probability of the empty set is 0. That is, the probability that none of the things happen, none of the outcomes, would be 0. We can use this definition to write a more generalized definition of the probability of an event. Probability of an event, generalized. Let S be a finite, non-empty sample space in which every outcome has a probability assigned to it by a probability function. If E is any event in S, the probability of the event E is the sum of the probabilities of all of the outcomes contained in E. So let's see if you've been following. Let's test the function shown here against the rules for a probability function. A sports analyst considers the strengths and weaknesses of the 4 remaining teams, and he suggests the probability for each team winning the championship. The problem is, if you add those 4 probabilities, it doesn't come out to 1. It comes out to 123 over 120. So this is not a good probability function. Remember, for a function to be a probability function, the sum of all the probabilities must be 1. It's not always easy to determine probabilities, but the arithmetic involved is fairly simple. You'll generally only need to add, subtract, multiply, divide, and count. Here's a good overview of the strategy. Strategy for determining probabilities. First, determine the sample space of all possible outcomes. If at all possible, choose outcomes that are equally likely. If the sample space has equally likely outcomes, the probability of an event, E, is determined by counting the number of outcomes in E and dividing by the number of outcomes in S, the sample space. If the sample space does not have equally likely outcomes, determine the probability function. Check to be sure that the conditions of a probability function are satisfied. Then the probability of an event E is determined by adding up the probabilities of all outcomes contained in E. Let's see if we can put the strategy into practice in the next example. Sal opens a box of a dozen chocolate-covered creams and generously offers 2 of them to Val. Val likes vanilla creams the best, but all the chocolates look alike on the outside. If 4 of the 12 creams are vanilla, what's the probability that both of Val's picks turn out to be vanilla? Well, first, each of the 12 chocolates is exactly as likely to be chosen as any other. So we want to count the number of ways that Val can choose 2 of the 4 vanillas, which is 4 choose 2. And we want to divide that by the total number of ways he could choose 2 chocolates, which is 12 choose 2. If I simplify, this becomes 4 times 3 over 1 times 2 over 12 times 11 over 1 times 2, which is 4 times 3 over 12 times 11, or 1/11. That's enough for our introduction. In the next video, I'll demonstrate more approaches to calculating probabilities, including Venn diagrams, tree diagrams, and conditional probability. Until next time, bye-bye.